In this video, we're going to further our discussion of using derivatives to determine the shape of our graph. In the last two videos, we were looking at intervals where the function had increasing values and the intervals where it had decreasing values. We had local maxes and local mins we were concerned with. But in this video and the next video that we'll look at doing, what we're going to do is we're going to take that a step further and not talk about just the first derivative for our function. We're going to look at the second derivative to determine different intervals of where f is concave up and concave down, and we're also going to look at where f has points of inflection. And the way that we do these two things is we look at, like I said, the second derivative. Okay? Similarly to how we look at critical points of our function to determine where f has a local max, local min, is where f prime of x is 0 or undefined. Points of inflection occur when the second derivative is undefined or the second derivative equals 0. So what we need to do in order to figure out where those happen is take the second derivative. And then what we're also going to end up doing is determining where f is concave down and concave up, and that's going to have where f double prime is negative is where we're going to have that f is concave down, and f will be concave up when f double prime of x is positive. So we're talking a lot about the second derivative. Let's go ahead and find it. So if we take f prime of x, we see that f of x is this, so we can use the power rule to take its derivative. So we'd get 24x squared minus 60x minus 42. That's our first derivative, but we were talking about using the second derivative, right? So let's take the derivative once again, take the derivative of our derivative. So we get 48x minus 60. So this is our second derivative. We see that our function, for our second derivative at least, is defined for all x's that we're dealing with, because again, we're on the interval of negative infinity to positive infinity. So this linear function here is defined for all of our x's, or defined everywhere really. So all we're really concerned with is where the second derivative equals 0. So let's set this equal to 0 and solve for x. So how it's going to look is we're going to get, adding 60 to both sides, we get 60 equals 48x, or if we divide by 48 on both sides now, 60 divided by 48 reduces to 5 over 4 equals x. So x equals 5 over 4 makes our second derivative equal to 0, so this is a point of inflection. What a point of inflection is a point inside of our original function's graph where the concavity will change from going down to up or from up to down. Okay? So now we need to figure out, breaking this function into our intervals. We're going to go ahead and quickly jot our number line to know what we're dealing with. Infinity, negative infinity, say this is 0. We have our point of inflection here at 5/4. We're going to break our original interval of negative infinity to infinity up into negative infinity and 5/4, and then we have 5/4 all the way to positive infinity. We're again going to use the same process of testing a value inside of this interval and this interval to see what our second derivatives, what the sign of our second derivative is rather, and then that'll tell us whether f is concave up or concave down. So inside of negative 8 to 5/4, let's pick 0. And inside of 5/4 to infinity, let's do something like 2. Just something simple that fits in that interval, nothing too backbreakingly hard in terms of plugging in the number and evaluating the value. So here, if we take f double prime of 0 and f double prime of 2, let's see what that evaluates to. So 48 times 0 minus 60 is just negative 60, so more importantly, the sign's negative. So negative 8 to 5/4, our second derivative is negative, so f is concave down. Okay, let's look at f double prime of 2. 48 times 2 minus 60 gives us 96 minus 60, or 36, and that's positive. So 5/4 to infinity, f double prime is positive, so f is concave up. And those are our solutions to this problem. When we're dealing with concavity, we don't have to worry about kind of the intervals of where they change from down to up like we did with the first derivative, because when we did with the first derivative, that told us when we had a local max or a local min, but our second derivative doesn't give us that information, so all we're really worried about is where the concavity changes and on what intervals it's concave down, what intervals it's concave up. So this example that we looked at kind of took that step further for us in a very kind of simplistic way, right? We were taking the second derivative of something that we could use the power rule on over and over again. In the next video, we're going to look at something of a function that's a little bit more complicated to take the derivative of, but we're going to figure it out together.